This lecture we focus on the dimension of a linear subspace, which is actually the number of elements in a basis. Before we are there, we should prove one another. Starting with the following. Let V be a linear subspace of Rn, and assume that we have P linearly independent vectors in V. And moreover, that V is spanned by Q vectors W1, W2 until WQ. Can we relate P to Q? Well, this theorem says that we need at least as many vectors to span a subspace than we can find as linear independent vectors. So consider, for instance, this matrix A, and it's easy to find two independent elements in the kernel of the matrix A, which are these, minus 3, 1, 0, 0, 0, 0, and 0, 0, 0, minus 2, 1, 0. These are clearly independent and elements in the kernel of A. Yeah, check it yourself. So in kernel of A. Then what does this theorem say? Well, in order to make a span, to span the kernel of A, we need at least two vectors, because we found two independent ones, and we need at least as many vectors to span the kernel of A. Well, in fact, you may prove that it's actually 4 that we need to do that. Also, if we look at the image or the column space of A, then we see here that we have two columns. This is the first column, this is the fourth column. These two columns are clearly independent, and in the image of A, the column space. So we need at least two vectors in R3 to span the image of the matrix A. Well, in fact, we may show that the number we need is actually 2.